recording. Okay. Okay, so cationic hydrolysis always produces acidic solution. Okay? Has anyone here heard of a sourpuss? No. Okay. Damn it. I was hoping that you would have, because it would be a good way to remember that cationic hydrolysis produces acidic solution, but since you've never heard of it, it just means a grumpy person. If you're a sourpuss, it means like you've always got a grumpy disposition, okay? But that's not helpful to you. I did also want to point out to you that sometimes people will look at this and they will say, oh, look, what did we make? We made NH3. What is NH3? NH3 is a weak base. And so they will say, oh, this solution must be basic. Is it basic? No. Anytime you have an acid, you make a base, right? That's just what acids do. They always make their conjugate base. You have to look and say, did it produce hydronium or did it produce hydroxide? You can't look at the substance produced and the other substance produced and say, oh, it's a base. No. Okay. Could you please write the hydrolysis reaction that occurs in a solution containing chromium? Try and do it without looking at your chart, just to see if you can. Is that what you guys got? Excellent. Okay. So we've dealt with cationic hydrolysis because there's really only those four. What are the four? Phe, al, creepy, and ammonium. Okay? Now we're going to look at anions. Does that mean if cations are always producing acidic solutions, do anions always produce basic solutions? Well, sadly, no. They mostly do, but not always. Okay, so anionic hydrolysis usually produces basic solutions. However, anions can also be amphiprotic. So amphiprotic ions could produce acidic or basic solutions, and that's just going to depend on their strength as an acid and their strength as a base. They'll be stronger at doing one or the other. Okay? Is a solution of KF acidic, basic, or neutral? Remember, step one, you always have to do the dissociation. So you have to dissociate that into K plus and F minus. I would say because you guys really know what you're doing, you probably don't have to write the dissociation because you can just probably see that you've got a K plus and an F minus, and you can go straight to does K plus hydrolyze, does F minus hydrolyze. But when I teach my regular class, I make them write the dissociation because otherwise they try to hydrolyze the compound, and that does not work. Or they dissociate it in some way that doesn't work because they don't have as much experience with dissociating things as you guys do. Okay? So now that we have our two ions, we ask ourselves, does ion A hydrolyze? Does ion B hydrolyze? Does K plus hydrolyze? K is a positive ion. Does it hydrolyze? No, it is not. Feel creepy. Nor NH4 plus. And if it's not one of those positive ions, it will not hydrolyze. Does F minus hydrolyze? What would we get if it reacted with water? We would end up with HF. And who else would we get? OH minus. What type of acid is HF? It is weak. Ooh, look, I even put a blank for it, weak. So is this going to happen? Yes. Okay, so the above equilibrium can be set up so hydrolysis does or does not occur. It does occur. And remember, do not look here and say, oh, we made an acid, therefore it is acidic. What do we look at instead? We look at the OH minus and we say, ah, OH minus is produced. Therefore, the solution is basic. In summary, if we assume that the cation does not hydrolyze, we'll look at what happens when both ions hydrolyze in a little bit. If the conjugate acid of the anion is weak, hydrolysis does occur and the solution will be basic. If the conjugate acid of the anion is strong, anionic hydrolysis does not occur and the solution will be neutral. And this is as long as the anion is not amphiprotic, okay? Assuming the cation does not hydrolyze and the anion is not amphiprotic, could you guys do example 5? So are we good up to step 3? So HCN forms, it's weak, so anionic hydrolysis does occur. Which ion did we produce, H3O plus or OH minus? OH minus, and therefore the solution will be basic, okay? And then if there was a situation where anionic hydrolysis did not occur, the solution would be neutral, but that's not what happens here. So basically, you say to yourself, does it occur or does it not occur? And then that's that. Can you do example 6? You might even be able to do this very quickly depending on how much you've managed to pick up on this. And if you're like, I feel lazy, I don't feel like writing this down every time, not feel creepy nor NH4+, just remember if you write it down every time, you will remember it. So if you have trouble remembering things, write it down. If you have no problem remembering things, do what you will. We good with that? Okay. Do you need to write this down every single time? No. If you can look at this and be like, calcium, not feel creepy nor ammonium, so nope. If you can just look at bromide and be like, HBr is a strong acid, nope. You can just be like, neutral, bam, it's neutral. Yes? This is, all this walking through is in case, you know, you aren't able to just see it like that, okay? But if you can just see it, then you're good to go. So try this one on your own. You can do it whatever way you want. You can do it intuitively. You can write out all the steps. Do it however you want to. Strontium nitrite. Yes. Nitrite, NO2. So if this were a multiple choice question, this is what my brain would do. Yes? My brain would be like strontium, not feel creepy, not NH4+. NO2, who's this conjugate acid? HNO2. Oh, that's weak. Yes, hydrolysis will occur. And anionic hydrolysis is always basic unless you have an amphiprotic substance. So cationic hydrolysis is always acidic. Anionic hydrolysis is always basic unless it's amphiprotic, in which case it's complicated. Okay? Okay, so cations give you an acidic solution, anions give you a basic solution, amphiprotic gives you a complicated situation. And you will need to compare. Anyone want to guess what you have to compare? Ka and Kb. And whichever one is stronger is the one that it mostly does. It does both. And don't worry, I'm not going to leave you hanging here. Okay, we're going to do examples like that. But if this was too freeform, too in your head at this point, feel free to go back to this process. Write the dissociation, right? So if I did that, I would be like, okay, I'm going to write the dissociation. I have SrNO2 goes to SR2 plus 2NO2 minus, and then I'd be like, okay, does SR2 plus react with water? No. Does NO2 minus react with water? What could it do? It could only accept a proton. Okay, so I'll make it accept a proton. HNO2, OH minus, okay. And at that point, I can say, is this strong or weak? That is weak. So yes, this happens. And what kind of solution did we get? We got a basic solution. Okay, so you can do it in a more formal, structured way if that works better for your brain just yet, because you've only just learned it today. Do you know what I mean? Yes. Yep. Although we have a common error alert before that. Oh, we already talked about this. Many students think that because we produced a weak acid, that the solution is acidic. But you always make an acid, yes. And anionic, it's going to be the same deal as if you have an amphiprotic ion. So you'll look at the Ka of one, you'll look at the Kb of the other and say which one happens more. And then it's going to be acidic or basic based on that. Okay? So just ignore that. There we go. Each side of a Bronsted-Lowry acid-base equilibrium always has an acid and a base, so it means nothing that you made a base. You should have made a base. Okay? Always just look for the H3O plus or the OH minus. Amphiprotic ions. Amphiprotic ions, how do you recognize them? Do you remember? Have a removable H. Yep. Okay, and we don't even have to worry about our weird little exception, water, because water is not an ion, and only ions hydrolyze, because hydrolysis is the reaction of an ion with Hydrolysis. What is it the reaction of? An ion with water to produce, and actually you could even just write H3O plus or OH minus. Generally, when I'm defining it, I would say an acidic or basic solution, but this is actually really nice because you're like, ah, that's what I'm looking for. I'm looking for the hydronium or the hydroxide. You should know that definition. Okay. So here we have sodium bicarbonate. Na plus. Can Na plus hydrolyze? No, it's not field creepy, nor is it ammonium. But we have HCO3. Now HCO3 can accept a proton. And act as a base, and in that case it becomes H2CO3 plus OH minus. HCO3 minus can donate a proton. And it becomes CO3 2 minus and H3O plus. So in this case we have OH minus produced, and in this case we have H3O plus produced. It does both, but it does one of them more than the other. So is HCO3 better at acting as an acid, or is it better as acting as a base? How can you tell? Well, we talked about that earlier. We can compare its Ka and Kb. What is the Ka of HCO3 minus? (5.6 times 10 to the negative 11? Yeah. Excellent. Okay. What is the Kb of HCO3? How did you do that? Yeah, and this is one of the places where it's really important that you have Ka of the conjugate acid, because it's so tempting to be like, oh, I've got Ka already. Wouldn't it be nice to just toss Ka down on the bottom there? Because I've already looked it up, but that would be wrong because it has to be the Ka of H2CO3. So that's going to be 1 times 10 to the negative 14 divided by 4.3 times 10 to the negative 7. And what do we get? Sorry, Ansel, what did we get again? 2.3 times 10 to the negative 8. And so we look at those two values and we say, which one is bigger? Kb, 2.3 times 10 to the negative 8 is bigger than Ka, 5.6 times 10 to the negative 11, and therefore the solution is basic. And if you have ever tasted, has anyone ever tasted baking soda? What does it taste like? It's yucky, it's bitter. Okay, because it is a base, or at least predominantly a base. And I think that's probably a good place to stop. Okay, because everything is here. Yeah, we'll leave that for next day. Okay? You have your test to study for tomorrow. Yes? You can come 10 minutes early tomorrow if you want to. Yes?